Hello, and welcome to Greg Does Physics. My name is Greg, and today we are going to be doing some physics. We're going to be starting with problem 3.10 today, and 3.10 says this. A uniform line charge, lambda, is placed on an infinite straight wire, a distance d, above a grounded conducting plane, i.e. we have this plane and the potential on that plane is 0. Let's say the wire runs parallel to the x-axis and directly above it, and the conducting plane is in the xy plane. A asks us to find the potential in the region above the plane, and part B asks us to find the charge density sigma induced on the conducting plane. Now, to do this, what we are going to do is we're going to use the method of images. And you may be asking, what is the method of images? Where does it come from? And the method of images looks like this. We are going to create an image, and rather than trying to solve our potential and rather than trying to solve our potential in this region, what we're going to do is we're going to create an analog situation and solve the potential in that. And what we're going to do is we'll say, okay, we'll still have our line of charge lambda, but rather than having this grounded conducting plane at v equals 0 in the xy plane, we're going to put another line, also a distance d, except below the xy plane, and that will carry a charge negative lambda. And the idea here stems from the corollary to the first uniqueness theorem that Griffiths gives us. And the corollary specifically says the potential on a volume V is uniquely determined if A, the charge density throughout the region, and B, the value of V on all boundaries are specified. So what that is saying is that if we have a potential if we find the potential for some situation, we want to find the potential in the region that's above the xy plane. And the idea is that no matter how we come to that potential, no matter how we solve that potential, as long as the potential that we find has the same charge in the region that we're looking at, which is that there's this infinite line of charge lambda, a distance d above the origin and parallel to the x-axis, which we do in this case. And as long as the boundary conditions are satisfied, which are in this case that the xy plane, anywhere where z equals 0 has a potential of 0, and then you'd also probably expect the potential to go to 0, say at far away in z or y. It wouldn't have the typical boundary condition of the potential going to 0 at a large distance r, just because this is an infinite line. So it's a bit of a unique situation. It's the kind of problem that can only happen in a textbook problem. But for that reason, we can't say that the potential is going to go to 0 at high r, because you could be way along the x-axis, which would still be a big R, but you could still be right next to this line charge and could still have a significant potential. Regardless, we're saying that in this situation, if we can show that, if we can find the potential in this region, and we know that the charge distribution is the same in the region of z is greater than 0 in both problems, as long as we can show that the potential satisfies the boundary conditions of this setup, that the potential, therefore, that we calculate in this case will be the same as the potential we calculate in this case in the region where z is greater than 0, because obviously the charge distribution below the xy plane is different. But that doesn't matter. The question only wants us to find the potential in the region above the xy plane. So with all that preamble being said, why don't we go ahead and start trying to calculate the potential of this setup. Now, if you watched my video on problem 2.52, part A, then you probably are already somewhat familiar with how we're going to go about doing that. But we could imagine using Gauss's law and creating a Gaussian cylinder that runs parallel to our line charge, and then uses Gauss's law to calculate the electric field that is going to be created by each of these line charges. So this is Gauss's law. And then, since we're saying that for the positive lambda line, of course, the electric field that's created by this is going to be pointing radially away everywhere from this line charge in cylindrical coordinates. And that is going to run parallel to our element of area on the surface of this Gaussian surface that we picked, which also is going to be pointing radially outwards everywhere. And so then we can take our electric field term out of this, because we also expect it to, the value of our electric field to be the same as long as we hold this, the radius of the cylinder of the Gaussian surface, that is, the same everywhere. So we can take it out because we can say it's constant, and we can say it's collinear with our element of area. And our element of area for a cylinder would be S, for some constant S, the S that we're choosing for our Gaussian surface, d phi dz, and then this 1 over epsilon naught. Our Q enclosed is just going to say, if we say that our Gaussian surface has a length L, then that would be lambda L, and so then that's E S, because that's constant, times 2 pi for our angle phi, and then our Z runs looking parallel to the cylinder. That is going to be the length L, 1 over epsilon naught lambda L. L's cancel, and therefore we can say that the electric field caused by our positive lambda line is going to be equal to 1 over 2 pi epsilon naught lambda over S in the S hat direction. I'm putting the plus on the S just to denote that this is the S from the positive lambda line, because we will find pretty much the same equation for our line charge down here. The only difference is that it'll be the radius going away from this line instead of this one, and also it'll be negative lambda. Okay, so what we can do now is now that we have the electric field, we can calculate the potential from that electric field, which of course is just given by this equation, E, the electric field dotted with dl, the negative integral of that. And in cylindrical coordinates, our dl would be ds s hat, and then the other phi hat, z hat terms. Since our electric field is only going to be pointing in the s hat direction, we only need to pay attention to this ds. And so then we can say that this is equal to 1 over 2 pi epsilon naught. And we can take out our lambda as well. ds over s plus. And so now this begs the question, what are we going to choose for our reference point? And we can choose our reference point to be the origin. Again, in normal problems, you'd often say your reference point to be, r approaching infinity, but that doesn't work since this is an infinite line charge. So rather what we'll do is we'll set our origin as a reference point, kind of like you do in problem 2.52, as I mentioned. And of course, in terms of s plus, the origin would be s plus equals d, since it's d away from this line. So d, and we'll integrate it out to, I'll put primes on here just to denote that there's a difference between these terms and what we're integrating to. And what is this? This is lambda over 2 pi epsilon naught. And of course the antiderivative of this is natural log. And we have this negative here. We could also put the negative in here, and that would flip the integration order, the order of the limits of integration, and so then we could write that like this. So this is our potential for the positive line charge. Similarly, our potential from the negative line charge would be the same, because again, our reference point, it would just be d, because it's basically the radius away from this line charge, and to the origin it would be d for both. Yeah, the only difference would be that you'd have a negative lambda, and this would be s minus. And so we'll recall that potential follows the principle of superposition, and so to calculate the potential of this configuration, we can just add up the contributions from each line charge, and then what we get is we get 2 pi lambda over 2 pi epsilon naught, and we would get ln of d over s plus minus ln of d over s minus. But if you remember your log rules, if we have a constant outside of the argument of our natural log, we could flip that into it as a power. And so if we have a negative, in the case of our negative line charge, then what that would do is that would put a negative 1 power in here, which would flip this fraction over. And so then what we'd be doing is we'd be adding ln of ds plus ln of s minus over d. And if you remember, if you add two logarithms with the same base e in this case, since it's a natural log, what you can do is you can put them all into one log and just multiply the arguments. So that would be d over s plus times s minus over d, and the d's would cancel out. So this is our potential. Now all that remains for us is just to put this into generalized coordinates, i.e. We could get this in Cartesian coordinates. So how are we going to get s minus and s plus into Cartesian coordinates? Well, we can think about it like this. For the positive line charge, we have s plus, and all you could do is you could do Pythagorean theorem. So if you have some s plus that runs away from this line charge, the magnitude of that s plus would be, since our line charge is on at y equals 0, one component would be y squared and the other would be z minus d squared. And hopefully that makes sense. You basically just have to look at, this. You can imagine if this is our lambda right here and we want to find our s plus, and this is our z-axis and this is our y-axis, and we want to put our s plus term in terms of y and z, then just Pythagorean theorem, it'd be y squared, which is this right here, and z minus d squared, which is this right here. S minus is going to be pretty much the same thing because you can think of it as down here. The only difference is that it'll still be y squared, but it'll be y squared plus z plus d squared to account for the offset that it is now below the origin rather than above the origin. And so then what we can write is we can write lambda over 2 pi epsilon naught ln square root s minus being y squared plus z plus d squared over y squared plus z minus d squared. But again, log rules, this is an exponent of 1/2 in here, and we can just take the exponents in an argument of a logarithm out and multiply that by whatever's outside, and so we can take that 1/2 out and make this into lambda over 4 pi epsilon naught ln of y squared plus z plus d squared over y squared plus z minus d squared. And does this make sense? Well, one of our boundary conditions was that we need the potential to equal 0 whenever z is equal to 0. And so if we set z equals to 0 in this one, what we'd be left with here is y squared plus d squared. What we'd be left with down here is y squared plus minus d times minus d, so still d squared. Those are the same arguments, so those would just cancel out to 1, and so then what we'd have is natural log of 1. But the natural log of 1 is equal to 0, so this whole thing is 0, and therefore our potential when z equals 0 is 0. So that's that boundary term confirmed. The other thing is that we also wanted our potential to go to 0 at great y's or great z's. And you can see that if you have a very large y compared to your z, then this term is basically going to be negligible, and you'll basically end up with just y squared over y squared. Again, that's 1. The whole thing is 0. Likewise with z, if you have a huge z, the minus d and plus d is going to become negligible, and so this whole thing will basically be the same as z squared over z squared. Again, that's 1, and again, that means that this whole thing is 0. So what this is telling us is that our boundary terms seem to be fulfilled, and this is a potential. We're saying that this is the potential for the region for z is greater than or equal to 0. And what we calculate this from is an area where the charge distribution is the same, where z is greater than 0. And so with our charge distribution being the same, with our boundary terms being the same, then we can therefore say that this potential has to be the potential for this setup, at least for z is greater than 0. And all we used to do that was just create a similar situation and took advantage of the uniqueness theorem, or the corollary to the first uniqueness theorem. So this is our answer to what the potential is for that setup. Now, part B wants us to find the charge distribution that's created on this conducting plane. And to get that, all we have to do is we have to use the equation that comes from dn, this equation, which comes from the discontinuity in the electric field across a surface. And so if our electric field below here is 0, then we could say then this equation basically just follows from that. I won't get into deriving this equation, but this is the equation we want. Of course, our direction normal in this case, normal to this this plane, is just going to be z, and we want to specifically evaluate this at z equals 0, since we want to see what's happening on the conducting plane. So then what we're going to look at is dv dz as z equals 0. Now let's do that. Okay, so we get negative lambda over 4 pi, epsilon naughts cancel out, and then we want to derive this with respect to z. So first it's going to be 1 over this argument, y squared plus z minus d squared over y squared plus z plus d squared, and then it's going to be equal to, and then it's going to be multiplied by the derivative of what's inside the argument. And since we have z terms both on both parts of this fraction, we're going to have to use quotient rule. And so then what we'll do is we'll do y squared plus z minus d squared times the derivative of this, which is going to be 2z plus d. Okay. And then minus, and then derivative 2z minus d y squared plus z plus d squared all over y squared plus z minus d squared. And now what we can do is we can plug in z equals 0, negative lambda over 4 pi. So y squared plus, so we plug in 0 here, we plug in 0 here. Both of these are going to end up being y squared plus d squared. So that just is going to become 1. Okay. So then y squared plus d squared here times 2d. And then plus 2d, y squared plus d squared again. And so then we could write this as 4d, since it's the same thing, we'd just be adding them up. And then below there would be y squared plus d squared. We can cancel these out. And then what we're left with is the 4's cancel out as well. And we're left with negative lambda d over y squared plus d squared. Okay. And there we go. And does this make sense? Our instinct should be that since this is a positive charge on the line up here, that on this conducting plane, what would be created is a negative charge. And so we can see that this is indeed negative. That makes sense. And we also expect there to be some d dependence, since you figure that if you move lambda farther away or closer to plane, that's going to affect how much where this charge is collecting on the conducting surface, and also a y dependence, since you figure that there's going to be less charge being created on the conducting surface farther away from our line charge. I say created, maybe it's more accurate to say sort of moved around. And so our instincts seem to be that that makes sense. And do the units of it make sense? Yes, they do. They do, indeed. And so, from what we can tell, it seems that this seems like a reasonable answer. And so it's this problem in general is just a great way to show the power of the method of images and how that stems from the corollary to the first uniqueness theorem that Griffiths gives us. And once we use that, we calculate the potential, and then once we have the potential, what we can do with that potential to, for example, calculate the charge density that's created on our conducting plane from placing this line of charge right above that grounded plane. And I think that'll be all. So, thank you for watching.